Okay, so we started here last time and we talked about this idea that in basic math you have the operator, the operands, okay? Two operands with an operator. And then we talked about different ways you can write that. And I described it this way, that this is what's called a prefix expression, a postfix expression, and an infix expression. We are used to seeing our math in this format, okay? But to the computer, it actually prefers one of these two formats, because the result of writing it in those two formats is you do not need to follow the standard BEDMOS formula with brackets. Because here you can see an infix expression, we have to put the brackets there, because if we didn't, according to BEDMOS, we would do 3 times 2 first. We would do this first. So we're using the brackets to override the precedence order, and as a result, do this first. But in a prefix expression, that's not necessary. If we write it this way, and again, you think of it using a stack, the object that we just coded, then it will perform that operation properly. Okay, so remember, here's how it goes. Okay, these items will be all inserted onto a stack. So 2, 3, 4 plus times. Okay, so imagine these objects are all stacked up. Okay, the way it then evaluates this expression, right? Because if we were going to evaluate our top expression using the math we know, we'd go, oh, okay, you go 4 plus 3, you get 7. And then you go 7 times 2, and you get 14. But we'd have to use the brackets to do that math. But with the computer, the way it does it with this prefix expression, okay, is it starts reading from the top of the stack down, okay, like this. And actually, I think I have this stack backwards. Okay, my apologies. 2, 3, 4, yeah. Well, it doesn't honestly matter. Okay? But basically, as it reads, okay, when it encounters a operator, it pops 2 off the stack, these 2 here, performs the operation, okay, and I've written this backwards. This should be the plus and this should be the times. Well, I'm off today. That's okay. Okay. So it pops 2 off the stack, performs the operation, 3 plus 4, and then puts the result back on the stack. So now our stack would look like this. Okay? And that's just by popping the stack. It then would encounter another operator right here, pop 2 off the stack, do the operation, and put the result back on the stack. And we'd still get the same answer as we got when we did it that way. Okay? So that's prefix expressions. Okay? Kind of interesting. Now I have a little animation that goes with this. So hold on tight. Here it comes. Can't remember if I showed this to you guys last period, but okay. Come on. Come on. There we go. Okay, so here it is. Here it should be, if all is right in the universe. And if this computer goes down today, things are going to be ugly in here. You may hear some inappropriate teacher language. Okay, here we go. So this is a simple one. -6 and 1. So to do the prefix operation, come on, come on. Just one sec. Zoom this recording. Okay. Okay, so here we go. Read from right to left. Okay? Push the operands on the stack. So I push a 1 on the stack, push a 2 on the, or 6 on the stack. Then, the way it works is, when your reading encounters an operator, pop 2 things off the stack and place the result on the stack. Okay? Let's try with a more complex one. With postfix, it's the same idea, just a different order to the algorithm. Okay? So now I'm reading left to right. I push them on the stack. When I encounter an operator, I pop 2 off the stack and place the result on the stack. Okay, let's make it a little more complex. Okay, So with a prefix operation, I read okay? So I'm reading from the right to the left. So I encounter a number on the stack, on the stack, on the stack. When I encounter an operator, I pop 2 off the stack, perform the operation, put the result on the stack. Then I keep reading. Next thing I read is an operator. Pop 2 off the stack, put the result on the stack. I have no more input here, so whatever's left on the stack is my final answer. Watch how it works with postfix. This time I'm reading the other direction. Okay? So now, put that on the stack, put that on the stack. I encounter an operator. Pop 2 off the stack, place the result on this stack. Go back to my inputs. This is a operand, so put it on the stack. Then I encounter an operator. Pop 2 off the stack, place the result on the stack. I have no more input here, so whatever's left is my answer. Okay? There is an algorithm here that we're not going to do, but this is also a way to turn the kind of math that you guys are used to, infix expressions, to postfix expressions. Okay? So I'll leave that to you. It's just something, again, it's just extra there, but this is the kind of stuff you can code. Okay? This is the kind of stuff you can, in fact, code. Now, sorry, I'm just turning the recording software back on. Okay. So the Q object. And that's the British spelling for it. For any of you who've been to England or London or anything like that, they use that word, Q. What do they use it for? A line, yeah. It's a waiting line. That's what it means. It's essentially a waiting line. So if you go to the bank in Britain, they'll say, oh, go get in the queue. Whereas here in Canada, we say, oh, go get in line. So it's a line. It's a waiting line. So it is described as a FIFO object. You may remember that the stack was called a LIFO object. The FIFO object essentially means the first one in is the first one out. So let's say I was selling tickets to One Direction at this store right now. Jack Gore would be running to the door right now and he'd be first in line. Whereas Kyle's a little slower, might wait. Every other one of you grade 12s is already lined up. And Kyle comes in to the end. Who's the first one to get tickets? Jack Gore. Jack Gore is the first one to get those One Direction tickets, and that's what makes it beautiful. All right, so what do we need for a Q object? Well, we're going to need some of the similar things that we needed with a stack object, but again, we're going to change the wording. We're going to need a constructor. We're going to need to add things to the queue, and we're going to use the words enqueue. And then to remove things from the queue, we're going to use the word dequeue. That's the method call we're going to use. We're going to have a front and back method, is empty and size. And we're going to do it by inheriting our linked list object. Now, have any of you ever encountered these words before, enqueue and dequeue? It used to be a very popular music software. Used to use those when you'd make playlists. But if you guys use iTunes, they don't use those words, I don't think. I don't personally use iTunes, but some music software used to use those words when you'd create playlists. Okay? Is enqueue it into the list and dequeue it. I think at one time Windows Media Player even used it, but I don't think they do it anymore. But those were words that were actually used. So the programmer's influence was actually showing up in the user side of the software. Okay, so let's do this. Let's get to our code again. So our big example that we've been working on, okay, we did write a stack object. Okay, so we're going to today create a queue object. So add a file to your project, a Java class, and call it a queue. Q-U-E-U-E is the spelling. Okay, and you're going to add that queue object to your collections package. So just like the stack object, it's going to go into collections. So we need a constructor, but this queue object, like the stack object, is type generic, and it extends our linked list object. Whoops. Okay? So just like the stack object, the queue object is an extension of the linked list, so we don't have to reinvent the wheel. And it's generic, so it can hold anything. Okay? So this is going to be a great object if at any point in your programming you need some kind of line. Okay? That's just a simple line. Like just a simple lineup of things. Go with the queue object. It's got the simplicity that you need. Okay? Now, like the stack object, we're going to write a couple default methods. So a constructor, okay? And again, we wrote these in the stack object. We're going to write isEmpty in size. Well, here's the good news. They are exactly the same. So if you want, go to your stack class and copy isEmpty, copy size, and you can even copy toString and clone. We'll have to modify them slightly. But I'm going to take toString, size, and isEmpty right out of my stack class into my queue class. Okay? So I have isEmpty, size, toString. The modification I want you to make in toString is just that little thing we did with override. Instead of putting the word stack there, put queue. Okay? So that's the only change we make in toString is we change the word stack to queue. And then we'll just take care of it by its superclass. And then with the clone method, you change the word stack here to the word queue, because that's what we're returning. A shallow copy of our queue object. Is it kind of appropriate today that I mentioned One Direction and the word shallow in one lecture? Or did I just insult some of you? I maybe insulted Jack a little bit right there. Okay? Maybe. I don't know. You guys don't seem like the One Direction crowd, but maybe. I hate to make those assumptions. Okay. All right. So that was super easy. Okay. Now as well, the constructor is basically the same as well. To construct a class, or sorry, pardon me, to construct a queue, I construct a linked list. So all I got to do is make a call to the super constructor. And we're done. Okay. So our super constructor is done as well. So easy. So all we're really left with is the two basic methods. To put things into the queue and to take things out of the queue. Okay? So we need a public void enqueue method that takes t data. And we need a public t dequeue method that has no parameters, that will return a value. Okay? These are the two methods we need, enqueue and dequeue. These will both be one line of code, but we have to think it out. In the way we worked with a stack is going to be different than the way we do it with a queue, because of the fact that it's not a LIFO object, it's a FIFO object. First one in is the last one out. Now there's a couple different ways we can write this, but you guys think of how we could write these? Okay, let's take a look at the stack object. When we added and removed from the stack, we said super.insert tail. And when we removed, we said super.delete tail. So we were always adding and deleting from the same side. And by the way, that could have been head and head. Didn't have to be tail. As a matter of fact, Jesse couldn't live with himself. He had to switch it to head because he just couldn't handle it. And I said, I agree with you. I'm good with that. So I'm glad to see you guys are becoming really picky programmers. So how will it look in queue? Well, it doesn't matter as long as we keep it straight. So why don't we think of it this way, that the tail, the head of the list would be like the front of the line. So when we enqueue, we're going to go to super, the super class, and we're going to insert to the tail. So the tail is like the back of the line. So whenever we put something in line, it goes to the back of the line, the tail. But when we dequeue something, we say super dot delete head. So we remove it from the front of the line. And we could have reversed both of those. We could have inserted to the head and deleted from the tail. Doesn't matter, as long as we keep it straight on our end. So the Q object is a much simpler object. It uses our linked list object, so we don't have to do any work, as long as we understand the functionality of the linked list. Okay? And then there was two other little methods that I said we should write, just for good measure. Public T front and back. Front and back. This is, again, like, so this would be the situation that we're all lined up for the One Direction tickets, and say Mika shows up late, and she's not sure if she wants the tickets. She's looking at the line. She could just look at the front of the line without affecting it, so she could see Jack at the front, and she could see Kyle at the back, and she doesn't actually affect the line at all. And then she walks away and goes, wow, and she's stunned by this. So what would the methods be? You guys answer this question. Okay. Well, we actually have a front method already. We built a front method into our linked list class. But is that correct? That would work too. Or we can just say super.get 0. But you know, we already did this. We made a front and back method. So why not just call them? But as long as they are correct, are they correct? Front says the data at the front of the list. The head data, that is correct. That's what we're looking for. So again, this is where, again, you got to be kind of careful about which ones you are using. Super.front and return super.back. Okay? And these are obviously override methods. You are overriding methods that have already exist within the linked list class. So as a matter of fact, it's kind of not something you even need to do because it was already happening. Okay? I'm not returning, you're right. Okay. And this has to be cast into data type T. Okay, whoops. So that's front and back. Very simple methods. And we're done. We now have a working Q object. It has the couple simple methods that we needed to do it. So let's put a test. Let's put it to the test. Let's put the Q to the test. So let's go to our main package and our little main class that we have in our main package. And this was us testing the stack, and it seemed to work. Okay? So I'm just going to delete some of this code and switch the word stack to Q. So Q stack. Now this will require an import. Make sure you are importing it from your collection. So when you go to the import statement for Q, okay, because notice there's already a Q object in the Java utilities class. Okay, so I can import it to from our class. I'm importing our Q object, not their Q object. Okay. You got lost. Okay. So what I've done is I've jumped over to the main class. Okay. And I deleted the code, and I'm switching that testing code to this. I'm going to make a Q with a line of code like this. So I'm going to say Q equals new Q. The light bulb will come up, and it'll ask you to import Q. Okay? Make sure when you import it, you're not importing it from like java.util, that you're importing it from your collections package. Did that help, Mika? Okay. So now let's test its methods. Q dot. Actually, before we test it, let's switch it from integer. Let's do a different data type. Let's do double. Why not? Let's do double. Equals new double. Because again, it's fun to try different data types. We've done string, we've done integer, let's do double. So I'm going to enqueue some data, like 3.14. So I've enqueued this number to my lineup, to the queue. So let me call it again. I'll enqueue another I'll do it twice, 2 more times. So I'll make this one 4.25, and this one will be 5.36. Oops. I just upped the number each time a little bit, right? So I'm going to throw these 3 doubles into my queue. So again, imagine the way the queue is visualized, right? So it's a lineup. So at the front of the line is 3.14. At the back of the line is 5.36. So if I output the first thing from that queue, if I dequeue, it should dequeue the thing at the front of the line. So I'm going to output queue.dequeue. Oops. So I'm dequeuing my list right here. So what that should print out is 3.14 because it's at the front of the line. This is very different than our stack object because it would have popped the last item in the list. So run it. Okay, and if all's right in the universe, I'm going to get 3.14 popping out here. Okay? Slow run, but it adds to the suspense of whether or not it works or not. Come on, NetBeans. 3.14. That's what we wanted. Okay? And then let's output the actual list. So we'll S out our queue, because we can easily turn the queue into a string. So I'll run it again. And here you can see the list. The list is got 4.25 and 5.36. Now remember, this is the front of the line up here. That's the back of the line. As well, when I dequeued 3.14, it removed it from the line. Okay? So now let me try one other little method call. I'm going to try and go S out queue dot front. Now front gives me the front of the line without removing it. So then I'm going to spit the queue out again and make sure that method is working. Okay? So here you can see it spit out 4.25. That is the front of the line, 4.25. So that's right. But then when it outputs the list, notice the list hasn't changed. So the call to the method front looks at the front of the line, but doesn't change the line. But the method dequeue gives you what's at the front of the line and actually removes it from the list. They're pretty simple, but I hope you guys understand the difference between those methods. Okay? Kyle. There's another word? It's in the wrong order. Oh, no. Okay, so let's double check. Is your enqueue, dequeue, and your toString method, it's all the same? Okay, so I'll come over and debug yours in 1 sec. I just want to try and wrap up stacks and queues with you guys. Okay, so in the notes, so I'm not banding you, Kyle. I'm just putting you on pause for a sec. In the notes is an example of code to write the queue from scratch. Okay? So just like the stack object, you can build a queue node. Now, if you build a queue node, it's a good idea to, this time, also keep track of a reference back and forwards, like we did with the linked list. So writing a queue from scratch is a little more work because you'd want to keep those double references in place. But after that, it's not too bad, right? So you'd have a constructor. You can see the constructor is very simple. You might override the toString method. That's pretty simple. Okay? And then the queue object, like our linked list, would use a reference to head and tail. That's easier. It would have a constructor, size is empty. Those would be pretty simple. toString method would be pretty simple. The enqueue method is a little more complex than the stack object because, again, you're dealing with 2 ends of the object, not 1 end. And same with the dequeue method. So we've already written these, so I'm not going to take you guys through the exercise. Know what's in the notes if you need it. Okay? Front and back, also very similar. There's also test code in there that tests both the queue and the stack there. Okay? And then in the notes as well, I also have what we just typed in, the idea of using inheritance to do it. Okay, last thing to cover. What would I use a queue for? Well, I think the queue is probably a little more self-explanatory than the stack object. But the queue object has many uses in computer science. That printer uses a queue. Maybe you've ever seen that on your computer, the print queue. The printer is a lineup. It just keeps track of print jobs as they line up. Okay? Simulations, like doing traffic simulations, obviously with a traffic light, you might need a queue object. Most computers use queues for processing, so they know sort of the order of processing, and that takes us back to the last piece of the IB hardware unit we looked at, that idea of processes lining up. The queue is the object that does that, right? Networking, when you send an email, it's packaged in a queue. So servers dealing with login requests, deal them in order. So queues are all over the place in computer science, okay? What it's queuing and what it's enqueuing and dequeuing depends on the problem itself, okay? Probably when we wrote our linked list, you imagined what it was going to be used for was a queue, right? Like it's just this lineup of stuff. But then once we had added methods like insert before and insert after, you kind of abandoned the queue idea because you knew it was better than that. But at its simplest level, a queue is just that idea of a lineup, okay? Now, queues can be varied. And again, this is nothing in the IB curriculum, but you can actually go beyond the queue to something called a priority queue. Now, I've programmed this, and I got the little story to tell you guys about this one. So I'm in computer science, and as you guys can tell, I'm an old guy. And back in the day when I wrote, we had dot matrix printers. Those are the really loud ones that you may still even have one of those at home where it brings a little print head across, goes, right? And the university was it was a really old one. So we would write our code, and we were in like a computer lab at the university. And then you'd hit print, and you'd have to go over to this big old printer, and it would print out your code. And it was on those pieces of paper that had little perforations, so you had to like rip them apart. They had little side. Have you guys ever seen these? Yeah, okay. So you know what I'm talking about. So, but the printer was so slow, and there were so many people in the computer lab that you'd hit print, and then you'd have to wait like half an hour because everyone was printing. You'd have to wait like half an hour to see when your thing would come out. It'd be very similar if all of you guys printed like 50 pages right now, and this printer was actually working. You'd all come over and stand here and wait for your particular 50 pages to come out. But this was way worse because it was so much slower. However, what we noticed in computer science was often professors would come down into the computer lab. They'd log in, they'd hit print, and then they'd just walk over to the printer, and all of a sudden their print job would be right there, and then they'd walk away. And we're like, how is that working? Then later, those sneaky buggers made us write the software that did that, and it was a priority queue. And what it was print jobs lined up in the queue, but when you sent your print job, it also sent a priority number with it. So as the printer got there, it went, okay, this is priority 5, so I'll just put it in the line. Oh wait, this job that just came in is priority 1. It jumps, it cuts the line. You guys ever done that at the cafeteria? Hey, can I cut? Well, that's exactly what was happening. The professors, when they logged in, had a different priority than me. And so as a result, their print jobs would cut the line. And they made us write the software that did that. So it was like this torturous thing that happened. Okay? So that's the stack and the queue. Okay? They are actually really useful objects in programming.